When most people hear quantum computing, they imagine something mystical, like Marvel's Ant-Man entering the quantum realm, science fiction, teleportation, or magical mathematics. But at its core, quantum computing is no longer a fantasy. It is physics and probability implemented through real-world engineering. A classical computer uses bits. Each bit is either a 0 or a 1. A quantum computer uses qubits. A qubit can be 0, 1, or a probability of both at the same time, a phenomenon known as superposition. And when qubits interact, they can become entangled, meaning the state of one qubit is mathematically linked to another, regardless of distance. So what does this mean in practice? It means quantum computers are phenomenally powerful calculators, capable, in principle, of solving certain classes of problems in seconds that would take classical computers decades or even centuries. These problems include molecular simulation, process optimization, cryptography, life sciences, and materials engineering. Quantum computers are not better at everything. To put this into perspective, if classical computers are trucks, reliable, versatile, and able to handle most workloads, quantum computers are space rockets, incredibly fast on a very specific trajectory, designed for specialized, one-off operations, and almost useless outside that narrow track. That distinction matters enormously. With such immense computational power, quantum computing has the potential to fundamentally change how the world operates, once the technology becomes reliable and scalable. And as investors, it is both pertinent and timely to ask, how should we position ourselves in the face of quantum computing? How do we capture technological upside without taking unnecessary catastrophic risk? Hi, I'm Freeman. Lately, quantum computing has become a hot topic once again. Countries around the world are actively pursuing it as a national strategic initiative, from the United States and China to the European Union, Japan, India, and even Singapore. At the same time, quantum-related stocks such as IonQ and Rigetti have been soaring. Naturally, friends start asking me the same question. So, who's going to win the quantum computing race? My honest answer is, I don't know. And anyone who tells you they do probably doesn't either. But not knowing the winner doesn't mean we do nothing. Instead, I believe the right way to approach quantum computing is to step back, slow down, and ask a much calmer question. How do we position ourselves in the midst of quantum uncertainty? This video is not about predictions. It is about strategic positioning. Investing in a way that allows us to benefit from quantum computing, regardless of how the future unfolds. Above all, this video is not financial advice and should not be taken as a buy or sell recommendation. I'm simply sharing how I think about risk and uncertainty. I encourage you to do your own due diligence and invest in a way that lets you sleep well at night. Broadly speaking, the quantum computing landscape can be divided into two camps. On one side are the big technology companies, most prominently Alphabet or Google, Microsoft, and IBM. These tech giants possess deep balance sheets, massive engineering resources, and patience measured in decades. On the other side are pure-play quantum companies, including IonQ, Rigetti, and D-Wave. These are smaller, more focused, and far more volatile, not just in stock price, but in long-term survivability. Before comparing them, we need to understand what big tech is actually doing, because despite surface differences, they start from a remarkably similar place. Across big technology companies, Alphabet, Microsoft, and IBM, quantum computing efforts are built on the same foundational approach, superconducting qubits. This convergence is not accidental. Superconducting qubits are currently the most engineerable and controllable quantum technology available at scale. They represent the most practical bridge between theoretical physics and real hardware. In simple terms, they can be fabricated using semiconductor-like processes. They integrate well with classical electronics. They can be wired, calibrated, measured, and scaled in controlled environments. For companies that already operate massive data centers and cloud platforms, superconducting qubits offer the best balance between speed, scalability, and ecosystem compatibility. But this shared foundation comes with unavoidable constraints. All superconducting-based systems share two defining characteristics. First, extreme cold. They must operate near absolute zero, requiring complex cryogenic infrastructure. This makes them expensive, fragile, and difficult to deploy outside specialized facilities. Second, short operating time. Quantum information degrades rapidly, noise accumulates, errors compound. Computation must be completed within a narrow window before coherence is lost. As a result, today's quantum computers are powerful but fragile, fast but short-lived, specialized, not general purpose. Big tech accepts this reality. Where they differ is how they respond to it. IBM takes the most pragmatic approach. It does not assume qubit instability will be solved anytime soon. Instead, it asks a different question. How do we extract value from quantum computing before it becomes perfect? IBM's answer is hybrid quantum classical computing. Classical computers do most of the work. Quantum processors handle narrowly defined subtasks where they add value. This allows IBM to focus on near-term enterprise use cases, such as portfolio optimization, risk modeling, logistics and supply chains, materials research. IBM already provides cloud access to its quantum systems, enabling experimentation today, even within current limitations. IBM is closest to immediate application, not because its quantum machines are superior, but because its expectations are realistic. Google takes a more engineering-driven approach. It accepts that superconducting qubits are imperfect, but believes steady improvements in fidelity, error rates, and control can push the boundary forward. This philosophy is reflected in Google's Willows roadmap, which prioritizes qubit quality over raw quantity. Google's belief is simple. We don't need perfect qubits. We need sufficiently good qubits, engineered at scale. Its efforts align with problems where accuracy is critical and complexity explodes at scale. Google represents disciplined long-term progress, not immediate commercialization, but a credible path forward. Microsoft stands apart. While it works with superconducting systems today, its long-term bet is on topological qubits based on exotic quantum states. Instead of fighting noise with layers of correction, Microsoft is attempting to eliminate the problem at the physics level. If successful, error rates could drop dramatically, error correction overhead would shrink, and scalability would improve. But the risks are enormous. The physics is extremely hard, progress is slow, and timelines are unclear. Microsoft is effectively saying scaling fragile qubits is pointless. Fix the foundation, even if it takes decades. This is a true moonshot. Pure-play quantum companies exist solely to build quantum computers. They are smaller, more specialized, and far more exposed to technology and financial risks. The most visible names include IonQ, Rigetti, and D-Wave. Each follows a distinct technical path, and each faces a very different commercialization challenge. IonQ adopts trapped ion systems, which offer exceptional qubit stability and long coherence, often orders of magnitude longer than superconducting qubits. They operate near room temperature, but rely on extreme precision, lasers, vacuum systems, and electromagnetic traps. They are accurate, but slow and hard to scale. Rigetti uses the same superconducting qubit physics as big tech. It focuses on hybrid workflows, similar to what IBM is doing, combining the quantum computer with the classical computer to solve real-life problems. Ambitiously, Rigetti is aiming to be a full-stack quantum integrator, developing its own hardware, software, and control. Given that its business highly focused on quantum, Rigetti has no luxury of time, unlike the big tech. It needs to extract value from imperfect quantum fast before its investors run out of patience. D-Wave uses quantum annealing, which is a noise-tolerant approach. The beauty is that it avoids error accumulation and does not require fault-tolerant correction. But by nature of its physics, it can only be designed specifically for optimization problems, so it is not going to be a universal quantum computer. Its quantum technology is considered close to commercialization, but only within a narrow niche. After reviewing the landscape, we can draw deductions, not predictions. What do we know about quantum computing? There is no single quantum computer. Quantum systems are extremely fast, but only briefly. They are not general-purpose machines. They are extremely expensive to build. They are even more expensive to operate. We are firmly in the NISQ era, noisy, intermediate-scale quantum. What we don't know about quantum computing. First, the winner, which architecture will ultimately be embraced in scale. Second, the timeline. When can we or could we even ever exit the NISQ stage? These are structural uncertainties. Here is the key idea. Quantum computing is real, powerful, and strategically important, but it is also early, expensive, and deeply uncertain. When outcomes are uncertain, you invest in companies with optionality, not in predictions about which outcome will prevail. Pure-play quantum companies are highly focused and therefore fragile. They cannot afford to be wrong. In my view, these are more suitable for venture-style investors, where capital is explicitly allocated for high risk and high uncertainty. Big tech, by contrast, has three advantages: strong balance sheets, durable cash flows, and long development time horizons. If quantum computing succeeds, they benefit. If it fails or takes far longer than expected, they continue to compound through their existing businesses. This is optionality without existential risk. And in my view, big tech offers a much safer way to gain exposure to the quantum wave. Among them, Alphabet appears the most balanced, not as a prediction, but as a relative assessment. It combines engineering depth, financial strength, a pragmatic technical approach, and powerful ecosystem leverage. The above reflects my personal framework for thinking about risk, survivability, and optionality as an investor. Above all, nothing discussed here is financial advice or a recommendation to buy or sell any securities. All views expressed are for educational purposes only. Please conduct your own independent research before making any investment decisions. Goodbye, and have a great day.